Good morning, everyone. I'm Claudia Cavallaro from the University of Catania, and my poster is titled From Theoretical Optimization to Real-World Applications, Centrality-Based and Heuristic Approaches for Anomaly Detection, Complex Networks. The first one, published in Computer Operation Research, is Minimal Stable Feedback Arc Set and Graph Centrality Measures. The second publication of mine, From Structure to Suspicion. Cross-sectional detection of fraudulent behavior, a real-world signed graph, presented at SECET 2025. Although the topic differed, both works shared the same core idea, using graph structure and centrality to extract minimum information from the complex network. A minimum feedback arc set, in short MFAS, is a well-known complete problem. Given a directed graph, the goal is to remove the smallest number of edges to eliminate cycles. This is important in many settings, such as search engine ranking, circuit design, problem verification, deadlock resolutions. Graphs are powerful tools for describing complex systems, including finance and social platforms, where detecting anomalous nodes can help identify fraud or misinformation. Centrality measures such as degree, closeness, betweenness, eigenvector centrality, and PageRank provide interpretable indicators of which nodes are structurally important. The first study was tested on benchmark circuits, including IBM test cases, to evaluate the efficiency and the scalability of the proposed heuristics. For anomaly detection, I used two real-world trust networks, Bitcoin Alpha and OTC. These are signed and directed graphs where each weighted edge represents a trust or distrust rating between users. This dataset also includes ground truth labels, distinguish reliable users from potentially fraudulent ones, which makes supervised learning possible. For the minFAS problem, I designed a heuristic based on centrality measure and vertex orderings. The algorithm removes forward or backward arcs in a way that minimizes the number of deleted arcs. A key contribution is the definition of minimal stable feedback arc set. A set is minimal if no remove arc can be introduced without creating a cycle. It is stable if, for each node, removing outgoing arcs do not exceed the remaining incoming ones. These properties are distinct. A set can be minimal but not stable, or stable but not minimal. Experimentally, applying our minimization stabilization strategy reduced the size of the feedback arc set of about 17% on average. In the second study, weighted centrality measure was computed for each user. Then, Markov clustering was applied to identify communities. When users with similar centrality fall into different clusters, this may indicate suspicious behavior. These structural features were combined into a vector and used to train machine learning classify. A key experiment tests cross-network generalization, training on alpha and testing on OTC and vice versa to simulate deployment on different but related marketplaces. For the MFAS problem, the proposed heuristic proved fast, scalable, competitive with the state-of-art approach. In the anomaly detection study, the combination of local, global, and community-level structure yielded excellent performance in classification, performing early approach. This cross-network generalization is also particularly important. In summary, this study demonstrates how insight from graph theory can directly support practical anomaly detection in real-world networks. Centrality-based structural analysis provide a powerful information and interpretable foundation for both tasks. Thanks.